Hello everyone, welcome to the second day of the workshop. We will start with our keynote speaker Lutz Trahms from PTB Berlin. He will talk about magnetic nanoparticles in biomedicine, how magnetic measurements support their applications.
Thank you, Nina, for this kind introduction, and thank you for inviting me to give this talk. And I really appreciate to see so many of you here this morning after this beautiful night on the boat. So I hope you all have slept well, and I can continue. This is a workshop on magnetic particle imaging, and I am not going to talk about magnetic particle imaging. I'm going to talk about other methods, basically. Maybe briefly I will also touch the MPI, but not at the main topic. So I'll start with the physics of magnetic nanoparticles and a couple of applications in biomedicine. And then I will come to a couple of well-established techniques, magnetic measurement techniques that may help to give information that is needed for these biomedical applications. And in particular, I will address the biodistribution and quantitative imaging. Okay, let's start with physics. Magnetic nanoparticles are small particles made of some ferromagnetic material, such as iron oxide or so. And if they are smaller than 100 nanometers or so, then they consist of a single domain. And depending on its size, this single domain can be blocked inside of the particle or can be moved freely. And also blocked particles, in the case that they are suspended in a fluid, behave superparamagnetic and therefore react immediately to the magnetization field. Immediately is not quite true, but let's say very fast. Magnetic nanoparticles have other properties that makes it particularly suitable as smart probes in biomedicine. That is their size. They are much smaller than cells usually are. They are usually larger than most molecules, but they are in the size of genes, proteins, or viruses, and that gives them the chance to interact in the metabolic play that these molecules play in vivo. And our goal is to measure their physical, particularly their magnetic properties, and to understand how they work in particular biomagnetic applications. And a few of them I want to address are magnetic drug targeting, magnetic thermal ablation, and magnetic faction. Let's start with magnetic drug targeting. You've heard about this already yesterday by Professor Alexiou. And this technique is basically due to the fact that when brought into a magnetic field gradient, they can be, they are drawn or they're kept, they undergo translation or are kept from the translation. And this is a ferrofluid with a very, very high concentration of magnetic nanoparticles, but the same applies, of course, also to less high concentrations. And this is utilized in magnetic drug targeting, where a magnetic field gradient is brought in the vicinity or inside the tumor. And if the field gradient force is stronger than the blood flow force, then the particles are kept in the tumor. They can release their cytostatic pharmaceutical and kill the tumor and let the rest of the tissue more or less unspoiled and unaffected. Here you see how this works. This is a preparation of the tumor, and you can see already by sight that the nanoparticles are accumulated here. And this is, of course, a very rough picture, but this can be studied in more detail using magnetic measurement techniques. Magnetofaction is basically magnetic drug targeting in a micro scale, where in the scale of cell size, this force is used to increase the effectiveness of the compound that is attached to the tumor. This is a nice example that was made in the group of Alexander Pfeiffer from the University of Bonn, who has attached a gene to a nanoparticle, a gene that produces or is able to produce chromophores that create fluorescent reactions. And when brought into a magnetic field gradient, then they penetrate the cell wall and come to the nucleus, and then this protein is expressed. And you can see here nicely the correlation between the number of magnetic particles and the fluorescent effect that is seen in these optical pictures. Hypothermia, we heard about this also recently. Magnetic field, an alternating magnetic field is applied, and that shall heat up the nanoparticles and again leave the tissue, the healthy tissue, more or less unspoiled. In the study of Igor Tilda from Jena, you can see when it is applied to a mouse that inside the tumor, where the particles are accumulated, you see a heating up of several degrees, while in other sides of the body the temperature remains more or less unchanged. The issue here is that we have to control the temperature very carefully, because in some cases you want to apply apoptosis, which is the programmed cell death. In other cases you want to destroy the tumor tissue completely, and that is if you reach temperatures which are highly above 554, 44 degrees Celsius. And this is already applied in clinical studies of Andreas Jordan in Berlin to glioblastoma patients, prostate cancer patients, and others. One thing that is very important here is to control the heat up of the tissue. And this means there was a consideration a couple of years ago by Rabin, which says that we need certain concentrations of, say, 1% in order to reach temperature, a reasonable temperature increase by at least 1 Kelvin. The main point is here that the diameter of this concentration has to be in the size of 1 millimeter or larger. If these accumulations are smaller, then all the downloaded heat radiates away, does not significantly heat up the tissue. So what we need to understand the action of magnetic thermal ablation is that we need an image of the distribution of magnetic nanoparticles with a resolution at least in the range of a millimeter. Otherwise, we will not have sufficient information to judge whether the distribution of the particles in the tumor is sufficiently dense. Okay, so this is the issue. We have to deal with these applications in biomedicine, and what we need is physical characterization of the particles. We would like to know where they are in the body, and the best, of course, would be to have a quantitative picture of their distribution. So the oldest technique to study magnetic nanoparticles or any kind of magnetism is magnetic susceptibility, and commercial susceptometers are available since, I don't know, 40 or 50 years or so. And they are built up quite simple. We have a sample, we have applied a magnetic field, which should be more or less homogeneous, of say a Tesla or half a Tesla or something in that range. And then we have a squid that is inside of this magnetic field, and if the field is static and constant, then the squid will not see anything, except a little bit of noise, of course. And now we move the sample through this tissue, and due to the susceptibility of the tissue of the sample, we observe this magnetization curve. And the amplitude that we can observe is the quantity that we want to measure. And we have to do this for any field. And then we obtain curves like this. We have seen a couple of these curves already yesterday. And depending on the size of the particles, the slope and the saturation magnetization is different, so that one can conclude from these curves what kind of particles are inside the sample. Saturation magnetization is one quantity that we derive from this, and the initial susceptibility is another one that is very useful for analyzing the particles. And you can see here that we have analyzed a couple of different particles using this method, and from these data we can derive the saturation magnetization as well as the mean diameter, as well as the broad or width of the distribution of their size. This is a, I think, very interesting study that was done by a few years ago. He studied reservists in this way. And you can see that this is again such a nice curve. And if you fit this curve according to the procedure I've shown you before, we end up at a diameter, mean diameter of 7.7 nanometers in the very broad distribution indicated by sigma close to 1. This does not make sense, because we know that the particles in the list are much smaller than 7 nanometers. But if you look very carefully at its fit, you see that it deviates from the reality only slightly, but if you measure carefully, you see that there's a systematic deviation. And if we fit this by a bimodal distribution, by 2 different size maxima, then we end up at a diameter of about 5 nanometers and a second diameter of 23 nanometers, which we interpret to be the clusters or aggregates of these particles. Another study by Lutz addresses the emotional behavior of the particles, and he has compared the behavior of particles in a fluid and in gelatine with what we see in the tumor. You see that the blue curve resembles very much the curve of the gelatine, and it has nothing to do with the curve in the fluid, so that his conclusion is that we have an immobilization similar to what happens in the gelatine when we apply magnetic nanoparticles in the tumor. Asymmetric stability is another very old technique, which is basically very similar to M/H, except that we have an alternating field. The field in this case is not very strong, and we see the absorption at different frequencies of the sample, which obeys the well-known laws, and the maximum of the imaginary part can be identified with relaxation time, and from this we can conclude on the size of the particles and on the viscosity of the medium. Also a very well-established technique that is known for many, many years. Let me now come to magnetorelatsometry, a method that was invented in my lab some 20 years ago. And let me briefly explain what it's like. Again, it's simple in principle. We have a sample in a coil, and we magnetize the sample in this coil for a period of, say, 1 second or so. And then we switch off the magnetic field and let the sample relax. And now we observe the relaxation with the squid, which is a very sensitive magnetic field sensor. And the difficulty here is to have a squid and have a setup in general which allows you to measure very soon after you have switched off the field, because we are talking about fields in the millitesla range, and we want to measure fields which are in the pico or even femtotesla range. And this is a challenge, but it can be solved, and it is possible to measure the relaxation after a dead time of, say, 200 microseconds or so. What happens in the sample? Well, in the sample, usually the magnetic moments are irregular, so there's no net magnetic moment. After magnetization, we have a net magnetic moment which relaxes with a typical relaxation time, and this is measured at a distance by its magnetic field. And let me explain what happens in some detail. We have a magnetization as a function of time. Let me start with the relaxation. That is this expression here, which is governed by the relaxation time, which depends on the size of the particles, on the anisotropy constant, and on the temperature. And so it gives you a lot of information about the particles that we are dealing with. This is what we have seen before. This is a magnetization that takes place when we apply the magnetic field given by this Langevin function that I described before. And we have to consider, of course, that we magnetize only for a relatively short time, and we might not reach the full magnetization in 1 second. So we also have to consider the magnetization process, which may not be quickly complete to saturation magnetization. And then we have what we are interested in, and that's the distribution of diameters or magnetic moments that can, for instance, more or less well be described by a log-normal function. So altogether, it's a complicated formula, but it can be solved, and from data, by fitting the data to this formula, we obtain information about the mean diameter, of the width of the distribution, and others, and we can compare this to what we have derived from M/H measurements, and this agrees quite well with the uncertainty, and it also agrees quite well with TM distributions that are given by this histogram. Up to now, I have not discussed the point of relaxation that can be occur in two ways. Near relaxation is the relaxation of the magnetization vector within the particle, while Brownian relaxation is a relaxation of the particle as a whole. And these two relaxation processes compete, so that if we have a particle that is moving in a liquid by Brownian process, and we attach something, some molecule or so to the particle, then it might undergo a slower rotational diffusion. And if we fix it to some wall, to the tissue of the vessels maybe, then only menial relaxation remains. And from such a process, we can see a change from these two relaxation behaviors. This is the Brownian curve, this is the linear relaxation curve of the relaxation time as a function of diameter. And a change in the mobility may have a dramatic effect on the relaxation time that can be observed, as we show in this example, where we see as a function of concentration of nanoparticles in the special medium, this dramatic increase with the concentration that goes down again with the concentration of the analyte. And this can be explained by the rotational diffusion of the particles when molecules are attached to it, which might result in a network at a certain amount of concentration. And again, if these particles become saturated with these attached molecules, then they become loose again and the relaxation gets faster again. Okay, this is as much as I wanted to tell you about the about the characterization of the particles, of the motional behavior. And I would like now to come to the important point of biodistribution. How are the particles distributed in the tissue of the patient, or in this case of the animal? We want to have the particles in the tumor. We do not want to have the particles, say, in the liver or in the spleen. And what we need, again, are measurements. And there's a couple of studies that have been taking place with magnetoreximetry, where we could show, in this case it was on a mouse lung, that they, when magnetic drug targeting is done, this was a study by a group of Carsten Rudolph in Munich, that the magnet focuses the magnetic nanoparticles to the right lung where the magnetic field was applied, and we can measure this very precisely with magnetoreximetry. We can observe the animal as a whole and have an idea about its location as well as about the magnetic moment that the particles make up altogether inside of the animal, accumulated at some place in the tumor. When comparing this to a reference, we can give the exact amount. And the nice thing here is that by such a measurement where we localize the position of the tumor, we do not have to narcotize the animal, but you can move freely around. We can attach or assign a location to the animal, and for each location we can control the value of the magnetic moment. And this gives us a chance to leave the animal consciously and observe it for a long time. This was a study we did together with Ingrid Hilger from Jena. And you see here that we observed these mice for 1 week, I think. It was, yes, 1 week. And we could observe the amount of particles in this animal for this whole time. And this animal was treated with hypothermia, and so this longitudinal study could be accompanied by magnetic relaxation measurements that made sure that the particles were not disseminated from the mouse. Finally, I would like to touch quantitative imaging. I will not talk about MPI, I will talk about magnetoreximetry in this case. The simplest thing that we have applied in the measurements I showed you before is we magnetize the whole animal in a high magnetic field, for example, by using Helmholtz coils, and we have a multi-slit array that measures the magnetic field that is emitted by the animal after the field is switched off. And then we can see something like this. This is a magnetic field distribution. It's not the nanoparticle distribution, but we see that it is distorted. It's not a simple magnetic dipole, but somewhat distorted in this direction. And from this we can roughly estimate that there is a second source in the range of 15% or so, which is in this case very likely the liver, so that only 85% have reached the tumor. This was done again together with Christopher Alexiou. But this is not so satisfying. I mean, the uncertainty is very high and it's not a clear image, it's just a localization. And so we have been thinking about, for the last few years, in fact, this is the dissertation work of Mike Liebel from our group. And we have thought about methods how we can improve this technology. And basically we want to create an image of the magnetic nanoparticle distribution in a volume that is made up by a number of voxels. And for a single voxel, we have that the signal that we observe in magnetic relaxation is somehow proportional to the concentration of the particles in this volume, in this voxel, and of course by the magnetic properties of this distribution of particles. And now we have an array of squares of very sensitive sensors of a magnetic field which have different locations, and so they generate a field that can be calculated and measured by simple physics of magnetism. And again, it's Biot-Savart's law. We have not only one magnetization coil, but a couple of magnetization coils, which do not generate a homogeneous field, but a highly inhomogeneous field, but a field that we know. And we can magnetize the sample by a couple of different fields. And altogether, we then have a function that describes the distribution of the particles by two functions F1 and F2. And altogether, we can solve this set of equations to interpret our measurements, and we end up at an image of the particle distribution. We have done this up to now in a phantom. This is, as you may realize, not a living animal, although we tried our best to let it look like a rabbit. And we have put some drawers into this rabbit, which is ethically allowed in this case. And we have our multi-channel sensor, which contains 300 squids or so. This is a more detailed picture of our phantom. And then we have a couple of excitation coils, an array of excitation coils above and below this sample. You see these are spherical coils which generate a well-defined field. And then we have tried to image the letter P. P stands for PTB, not for Philips. And you see it works quite well if we are close. Well, this is a set of drawers, as you can see here. This is the upper drawer, which is filled with the P cubes. And if we go lower, the image gets worse, the errors are higher. This is the worst case actually in the middle, where both excitation coil sets are the farthest away. And it gets better again if we go down to the lowermost set of excitation coils. Okay, this is my contribution to MPI. We have an MPI, as I think it has been said a couple of times already in the last few talks, that is running now. I think Ulrich Heinle said it was made up in December 2015. I would say it starts running in February, March 2015. Anyway, it's running now, and we are working together. This is what I've got from my lab, and it's Dr. Now from the Charité. We work together now. And our goal in this case is our PTB's goal in this case is to study phantoms and study the relation between the physical properties of the phantoms, of the particles and the phantoms, and the image that we obtain in order to transfer MPI to a real quantitative imaging technique. So we don't have any results about this, and this is why I've been talking about other techniques up to now, but I hope next year I will be able to talk also about results with MPI. Well, the message that I would like to give is that the magnetic particles can be characterized by a variety of magnetic measurement techniques, magnetic susceptibility, magnetolensometry, and magnetic particle spectroscopy, which I did not address in this talk, but later on in this session there will be a talk on how we apply NPS for characterizing and analyzing and quantifying magnetic particles. Biodistribution imaging can be done by MRX, not so well, not so well, time resolved and spatial resolved, but quantitatively, that's the main point, and of course by MPI. And the message I would like to give in my talk is that we have a couple of biomedical applications of magnetic nanoparticles. And if we want to help with these applications, to make them work and to understand how they work, we have to use these techniques, and we have to adjust our techniques to the needs that are given by the biomedical problem. So there's of course good reason to adjust or to find the best traces for MPI and other methods, but in some cases the particles are there and they are adjusted to the application, and what we have to do then, what we physicists and technicians have to do in that case, is that we have to adjust our method or modify at least our method so we can make images of these particles, no matter if they are the best particles or best traces for MPI or whatever. Okay, I would like to draw your attention to an issue of biomedical engineering. Some of you may remember there was a beautiful issue in 2013 that was edited by Trahms on MPI. And now we are in the lucky situation to have another topical issue in this journal on biomedical applications of magnetic particles in general. And I was very happy that I could convince a couple of very renowned scientists to give contributions of their current work, an overview of their current work over the last few years for this journal and for this issue. And I can say that the papers are now in the reviewing process, so that I'm sure it will appear within the next few months, maybe this fall. And I encourage you to draw your attention to this issue. I think it will be very interesting to all of you. Finally, I would like to thank the people who have been so kind to give me some material that I could present in my talk. I would like to thank the Deutsche Forschungsgemeinschaft for support, the Bundesministerium für Bildung und Forschung, the Bundesministerium für Wirtschaft und Energie, and the EU for their funding. And eventually I would like to thank my collaborators, and well, most of them are paid by these money that I get from these authorities. Thank you. Are there questions or comments?
Thank you for that. Regarding the script relaxometry, I have some question. The sensitivity of this script is 6 or 7 order of magnitude difference from the applying field, polarizing field. So in the case, how you are preventing from the flux trap, the script? You remotely polarizing and then move, or using some switch or current limiter in the flux transform?
Yeah. Okay, that's a very good question, and in fact this is a challenge. And in earlier years we just did not use strong fields, so we just didn't apply millitesla but only microtesla. That was the beginning, of course. The next step was that we used a setup which is different from what I have shown you, and we turned the sample around so that the magnetic field is not directed into the squid, so that the stray field of this magnetizing field is 2 orders of magnitude lower than the stray field at the sample. And then, well, we are in PTB, we are in a very lucky situation that we have colleagues. We do not develop the scripts in my group, but we have colleagues that are experts in script development. And they were so nice to develop scripts which are extremely insensitive to high fields. I mean, they're robust against high fields, they can measure it as well, but they have a particular design that makes them robust against high fields, and this is the final solution to this problem. So we are very, very safe, on the safe side now in this respect, but it has been a real challenge to this group. Yes,
Thank you very much for this very interesting talk. I would like to underscore your last sentence you mentioned in your talk. I compared a little bit the techniques presented yesterday and today with ultrasound in medicine. When you go 20 or 30 years ago, we had ultrasound and it was a very primitive compared to now the technique we have available for patients. And I think this is the same also if I want to address Philips or other technicians. We have to improve the technique on the one side and of course also the particles, but it's a vice versa process. And it's only possible if you have an interdisciplinary talk with physicians on the one side and physicists and engineers, and I think this is one of the most important, for the future topics we should address. We have a vice versa discussion. This is only possible interdisciplinary, and so we are lucky working together with you and also hopefully with the other partners.
Yes, I think that's absolutely right. I think we have to make compromises. We cannot, if you want to have the best particles for magnetic stripe targeting, then in most cases they cannot be the best particles for being seen by MPI. So you have to find some kind of compromise. And I think you have made already some progress in this respect, as I can learn from your talk yesterday.
Thank you for the very nice talk you gave and impressive work on, in particular, the DC split spectrophotometry. That's really impressive. But in terms of applications, I'm a little bit worried because if you look at a controversy that we had many decades ago between MEG with squid and MRI, the argument at the end for the MEG was that the signal was in the very low frequency domain given by the physiology. But in this case, you propose applications of particles which can easily be transported to the high frequency domain. Isn't that a much more viable route than your specific method, or do you see specific chances in your methods? That's what interests me.
Well, if you're talking about MPI, of course, then at present at least we are in the range of 25 kilohertz or even 150 kilohertz or so. And in that case, RF coils are absolutely the right device for the recording. But on the other hand, it might also be useful to turn down the frequency of MPI to lower frequencies to avoid a couple of problems that may come up in terms of the eating up the tissue or so, and other problems that might come up. And as I said to the question of Alexiou, in some cases we, for instance, do not need the high temporal resolution. If you want to know the distribution of particles in a tumor, you do not need any temporal resolution. It might be sufficient to have the recording time of 1 hour or so at the most. And so in that case we might find it a better solution to turn down the frequency to say kilohertz or even less. And then again, SWIFT might be the better, or any other sensor, atomic sensor, magnetometers also. I have no strong feelings for, not strong feelings for SWIFT, but I am open to others. But I'm open to other things as well. We just have to see the problem and then find a solution from the technology that is available. I think I'm not the chair of the session, but I think we should close.